Hi, I'm Alistair, and in this video I'm going to explain how you can create an escape room puzzle where players need to blow out candles. Now, having a real naked flame in an escape room is pretty dangerous, so I'm going to be using LED candles, but players still need to really blow on them to put them out. And if the players blow the candles out in an arbitrary order, not really much happens. After a short amount of time, the puzzle simply resets and the candles reignite. But if they blow them out in the correct order, then a relay is energized which releases a maglock, and that might contain a key or open up a new area of the room. And this is what you'll need to create this puzzle. I've got an Arduino Nano here, which is mounted to a sensor shield. Now this just makes it easier to plug components into the GPIO pins, but you can use almost any sort of Arduino for this project. I've got a 5-volt relay module, and that's going to be responsible for controlling power to the maglock and also releasing the lock when the puzzle is solved. On this side here, I've got a serial MP3 player component. Now, this is optional, but if you'd like to trigger a sound effect when the candles are ignited or when the puzzle is solved and they're all extinguished, this is the device which I'm using to do that. It has an SD card on the back of it, which you can save WAV or MP3 audio files to, and then you can trigger those sound effects to be played by the transmit serial connection, which is connected to the Arduino here. This will then play those sound effects through this 3.5mm headphone jack, through this red wire, and that is connected to a standalone amplifier and speaker, which I've just got off camera. And then the main component you're going to need for this puzzle is obviously 2 or more candles themselves. So let's take a look at those in a bit more detail. Now, you can make these candles yourself. You could 3D print them, or you could use papier-mâché, and then you can actually melt real candle wax onto the outside of them to make them more convincing if you want. But these particular units I'm here, these are actually sold as battery-powered LED candles, and I'm not actually using that much of the original components in them. If I just slide the insides out so I can show you what's inside. So here we just have the hollow exterior, and the most important thing about this is it needs to be slightly translucent, just so it's going to let the light from the LED inside just shine in the same way that authentic wax would. And then inside here, at the top here, this little kind of flame thing, this is purely optional. So the advantage of this is it gives a surface that the LED light can reflect off, and it looks quite good when the flame is lit. The problem is that when the candle is extinguished, it looks less convincing, because then you've got, as with this one here, you've just got a white bit of plastic flapping around. So it's totally up to you whether you want to use something like that or not. It makes no difference to the mechanics of the puzzle at all. It's purely aesthetic. So I've just left them in because I think they look quite good when they're lit. And then we've got 2 main components in the candle itself. Here we've got the LED, and if I just sort of twist the candle around and move the flame out of the way, you can just see that's just a regular LED in there, and that is wired. The cathode is going through to ground, and the anode I've got through a resistor, which is in this heat shrink tubing here. And then the sensor is provided by this little module here, which you can see was just housed in the center of the candle. Now, this is a sound sensor module. You can see it's got a microphone at the top of it, but rather than simply providing the output direct from the microphone reading, it's got a potentiometer here, and what it does, it compares the volume level read at the microphone to whatever the value is set on the potentiometer there, and it outputs a digital signal, either high or low, when the microphone volume exceeds the value set on the potentiometer here. So you can't use it for recording audio, this particular device, or you can use it as a sound trigger sensor, and that's exactly what we want to have in this case. Now you'll see it's got a little bit of black tape on there. The reason for that is because it has a fairly bright power LED. This green light here is going to be on all the time the sensor has power. Now maybe you want that effect. You know, this is a kind of a mystical kind of puzzle, and if you were using this in a haunted room, you know, kind of a medieval eerie effect, perhaps you'd want a slight green glow coming from the inside of your candles. But if you don't, I've just put some black electrical tape over the LED there, just so it doesn't interfere with the light. The other side of the board here has another LED though, and this is the one that we're interested in when it comes to setting the sensitivity of the sensor. So obviously we want these to detect when the player kind of puffs straight into the end of the candle and blows the candle out, but we don't want to be so sensitive that they're being set off by every sound effect in the room. You know, escape rooms can be quite noisy places. People could be shouting or you know, jangling keys or dropping things on the floor. So we're going to adjust the sensitivity to make sure that only direct input onto the microphone gets detected. And we're going to show you how to do that. So I've got a small screwdriver here, crosshead screwdriver, which I'm going to insert into the little potentiometer there. Now, if I turn it all the way anti-clockwise to start with, you'll see that this light is on all the time, and I've also just blown the candle out. So this is where it is at its most sensitive state. You'll see it's being triggered all the time, and when that LED is on, that means that a low signal is being written to the digital output line here. If I turn that clockwise slightly until the LED just goes off, what you should now find is it's now lighting up as I speak. So it's detecting my voice. When the room is silent, it's off, the LED is off and the line is high. And as I speak, that's making the LED glow and the line is going low. But I probably still want it to be a little less sensitive than that, because I don't want the candles to get blown out whenever anyone just speaks in the room. So I'm going to carry on turning it clockwise to make it less sensitive. And now, oh, a bit further than that even, what I'm trying to get to the point is that when I am speaking, or any other just ambient noise in the room is not setting the LED off at all, so we're not getting a signal here. But if I puff directly down the end of it, like that, you'll see that in that case it is being set off. So that's probably about right now. This is something you'll want to tweak depending on the exact environment in which you plan to use these sensors. But it's actually very easy to do. I've also, when I come to show you the Arduino code a little bit later on in the video, I'm also using a little bit of software debouncing to ensure that they're only set off by a continuous blowing across the microphone rather than a percussive sort of banging noise that sets them off. It needs to be a continuous blow like that that will trigger the sensor and cause the candle to go off. So here's how I've got the components wired up. At the top of the screen here, I've got my 4 candles. That's 4 candles, not fork handles, just to be clear. Each one containing an LED, which is going to create the candle flame effect, and also the sound sensor with the microphone on the top. Over this side here, I've got an MP3 player, and this is just going to provide some additional sound effects. One when the candles are reignited, when the puzzle is reset, and another one that will play when the puzzle is solved and the lock is released. Now this is completely optional. I think this puzzle already has quite a lot of visual feedback for players as it is, but it never does any harm to have additional audio sound effects as well, just to confirm when certain actions happen in the puzzle as well, just for players to get that secondary feedback. Over this side here, I've got a 5-volt relay module, and that is controlling a 12-volt DC power supply that's going to this maglock here, and that's going to be released when the puzzle is solved. Now, I've got all of these components shown wired to an Arduino Uno in the middle here. Now, in fact, you could use other sorts of microprocessor instead if you want, but the reason why I've chosen the Arduino Uno is because some of these components need to be wired to GPIO pins with particular capabilities, And unlike a Nano, the Uno actually labels those pins on the board itself, which makes it easier to check your wiring. So let me explain what I mean in a bit more detail. If we take a look at the candle LEDs, for example, you'll see that they've got the cathode, the negative leg of all of them, is wired through to ground on this black line here. And then the anode, the positive leg, each of them is wired through a 220 ohm resistor, and then they are going through to individual GPIO pins here. Now, if you just wanted to turn the LED on and off, what you'd normally do is just write a high value to each of the pins here. That would send 5 volts through the resistor, through the LED, it would light up. But we're going to do something a bit different. We actually want to create a flickering candle flame effect here. So rather than writing a simple high digital signal, we're actually going to write an analog varying voltage signal. And we're going to do that using something called PWM, or pulse width modulation. So rather than using the digital write command and just sending a high value, we're going to write an analog value somewhere between 0 and 255, and by choosing a random value each frame, we can make the LEDs flicker, which is just going to make them look a little bit more like a convincing flame effect. Now the problem with that is that PWM output, this analog output, is only supported on certain pins. And on an Arduino Uno, conveniently enough, those pins are labelled with this little squiggle symbol here. In fact, you can see on the board it says PWM equals squiggle. So pin 3, 5, 6, 9, 10 and 11 all support this variable PWM output. So we're going to use those pins to connect to the anode leg via a series resistor of each of the LEDs. Now the microphone sound sensors, well, these are going to just have a simple digital input coming into the pins. They're either going to read low or high depending on whether they've been triggered above their threshold amount or not. So they can go to any GPIO pins, and I've kind of just picked fairly arbitrary ones here that are next to the nearest LED pin that matches that candle. And obviously the sound sensor itself is also connected through to ground and to VCC 5 volts. So this red line here comes all the way around here and goes to 5 volts on the Arduino as well. Now when we come to the MP3 player, this too is connected to ground and 5 volts, and this is you command the MP3 player by using serial commands sent over these two wires here. We've got a receive and a transmit line. Now the problem is, and I've mentioned this in other videos, is that Arduino Unos and Nanos only have a single hardware serial interface, and generally speaking that's already being used up by the USB connector here. So to create a secondary serial interface to be able to send commands to the MP3 player, we're going to use software emulation, and I'm going to use a library to do that called AltSoft Serial. Now AltSoft Serial is a great library, but it only works on specific pins 8 and 9. So 8 is going to be the receive pin for our emulated software connection, and so it's connected to the transmit pin of the MP3 player. 9 is the emulated transmit pin, so it gets connected to the receive pin on the MP3 player. And those are pin definitions that you can't change in the library. It always uses those pins, so those are also fixed, just like the PWM pins. We didn't have a free choice of those either. Now coming down to this side, we've got the relay module. So this again connected to 5 volts and ground, and then it has a single signal line. Now this is a straightforward high or low trigger signal, so this can be sent from any output pin. I've got it connected to A0, which is labelled as an analog pin, but that just means that it has the capability to be used as an analog input. You can also write a digital signal to A0 just fine as well. So I'm actually using it as a digital output, not an analog input. And when a high or low signal is written to that, that causes the relay module to energize here. And inside it switches a connection that was connecting the common pin and the normally closed pin, and it switches it across to connect the common pin and the normally open pin instead. And what that means is that on the load side of the relay here, I've got a circuit that's got a 12 volt DC supply that's connecting this maglock here, and when normally closed and common are connected here, this is a closed circuit. The maglock receives power and it energizes and locks. When the relay receives a trigger from this A0 pin, it flicks across inside to connect common and normally open. Normally closed is no longer connected to the power supply here. This is a broken circuit. So this cuts the power and the maglock releases and unlocks whatever it was securing before. So that's about it. And here's the code that's running on the Arduino. So let me talk you through it. And we start at the top with two includes. So this is where we've got additional code that's been defined in another library somewhere else, but we want to bring it in and incorporate it into the code sketch here. And you'll see the first library I'm including is AltSoft Serial, and that was the one that we're going to use to define this secondary serial interface on a pair of GPIO pins that we're going to use to communicate with the MP3 player. Now, the AltSoft Serial library you can install from the Arduino IDE by going to Sketch, Include Library, Manage Libraries. And when the library manager comes up, if you search for AltSoft Serial in the search bar here, you'll find it is the first hit. It's this library here, and you can click to download and install it. Now, libraries that are downloaded in that way through the Arduino IDE, you include by giving their name inside angled brackets like this. These are libraries that are installed into your shared libraries folder, which is saved in part of your documents on your hard drive, and they're available to all sketches that you write within the Arduino IDE. Now, I'm also including another library here, but notice that this one is defined within speech marks instead. That's because this one is a local library, which I only want to use within this project. So I'll package this file up and I'll include it, and it's included in the source subfolder of the directory in which this sketch is contained. Now, I've done this in this particular way because in the past, some of my projects, I've suffered from the fact that I've distributed a version that works, and then sometime later, maybe a few years later, the library gets updated and changed. And perhaps the code that I wrote is no longer valid for the new version of the library. The advantage of using a local version like this is that is a particular snapshot of the library that I took at one version in time, and I know that it definitely works with the code that I've included in the rest of the sketch. If you include one of these more shared libraries, what you might find is that one of your other sketches might be written for version 1.5. If you then update the library to version 1.6, that will update the reference in all of the sketches that reference that library, because there's only one copy of it on your hard drive that's shared between all of them. And that might break some of your code later. So I'm pretty confident that this is a very robust, reliable library. I'm happy to use the latest version of that. But for something that is very specific to this project, I'm going to use a local library reference instead. So that's just the different reason for those two different syntaxes there. Okay, then we get on to the constants. So constants are variables that are not going to change, and I generally use this to define the pins that various pieces of hardware are connected to. So we're using 4 candles in this case, 4 candles. You can extend that to any number you want, obviously subject to having enough pins available to you. And remember, I mentioned that if you want the LEDs to flicker, you're going to have to use one of the pins that supports PWM output to power the LEDs on those pins. And there are those 6 pins available on an Uno or Nano. So I'm just using 4 of them here. You also then define the 4 pins that you want to use as digital inputs from the microphones. And we then define the order in the correct order in which we want players to blow the candles out. So for ease of use, I've referred to them as 0 being the leftmost candle and 3 going towards the right. Obviously this depends on how you have wired the order of the pins in here. And finally we define the pin that has the relay signal connected to it, and that's going to be the one that is driven high or low based on whether the puzzle is solved. So all these values here just reflect the wiring diagram that I showed you previously. So then we go on to the globals. So global variables are variables that are shared between various functions in the sketch and persist between them. So first of all, we define a global object that's going to be our software serial connection, and we also define a global interface to the MP3 player that is based on that serial connection. So from now on we'll be able to refer to an object called MP3 in our code, and it will control the MP3 player using that library we created that is based on the software serial connection, which are on pins 8 and 9. And then we define 3 further variables that are going to kind of control the flow of the game. So the first one is the step number that players are currently up to. So if we imagine this puzzle is requiring 4 steps, which are blowing out the 4 candles in order, we initially start off on step 0. So that means that they are at the beginning of the game. None of the candles are currently blown out. I'm going to create an array as well, and it's an array of Boolean values, so it's just true or false values, that lets us know at this point in time which of the candles are lit as well. So it's an array that contains 1 element for each candle, and that is simply going to say true or false for whether that particular candle is currently lit or not. And I'm also going to keep track of whether any mistakes have been made in following this sequence. Now there's 2 possible different behaviours that you might want in this puzzle when players get it wrong. What you might want is, as soon as they make the first mistake, you might want the puzzle to reset. So let's say players blow out candle 0 first, and then instead of blowing out candle 2 they blow out candle 3 instead. So they've gone wrong at the second step of the puzzle. We could make it immediately reset there, in which case they could probably find out quite quickly from trial and error what the correct sequence was, because they know that this one was right, and then they'll just try different values for this one until it doesn't reset, then they'll try different values for this one, etc. So that's one alternative, and you might want to do it that way. Or the alternative is to let players get all the way to the end of the sequence and only then unlock the lock if it was correct, or reset the puzzle if they went wrong at any point. So mistakes made is just a counter that I'm going to keep track of on the way if you want to implement that second approach, which is to actually let them go all the way to the end. But if they do so, let's take note of whether they went wrong at any stage along the way. That's what that counter there is doing. But we initialize it at 0 because at the beginning, they're at the beginning of the puzzle. They haven't taken any steps yet. They haven't made any mistakes either. So then we go on to setup, which is the function that's called when the program first runs. And we initialize the serial connection. Now this is the hardware serial connection. So this is the interface that uses the USB cable plugged into your PC. So if you've got the Arduino IDE running, as I do at the moment, and if you go into Tools, Serial Monitor here, you'll be able to display the output from the puzzle as it's running, and that's a really useful way to debug the puzzle and to see whether it's behaving as expecting while you're developing it. You wouldn't normally need to use that in a live escape room game once it's actually been deployed in production, but it's a very useful thing to have when you're developing things. And as all my code, I currently now do this at the very first line. So after creating the serial connection, the first thing I do is print out the name of the file that's running and the date that it was last compiled as well. That's just a really useful way of knowing what sketch is currently running on the Arduino when you have it connected through to the IDE. We'll initialize the pins, so we'll loop over however many candles we've decided to use in this puzzle, and for every candle we have one input pin, which is going to be what the microphone sensor is connected to, and we have one output pin, which is what the LED that's going to power the candle flame effect is plugged into. So we're going to initialize those in the default states. We're also going to initialize the pin that we're using to energize the relay lock. Now we don't need to explicitly initialize the pins that we're using for the serial MP3 connection. These pins 8 and 9 here, we don't need to explicitly call pin mode on those because that will be done for us when we start the software serial interface, and that's what we're going to do in these lines here. So we create our serial interface at a baud rate of 9600. That's the speed that is most commonly used to communicate with these kind of MP3 boards. I will be almost certain that will be the speed that you'll find, not just the exact board I've used, but any similar boards almost certainly will use that speed as well. So we begin the software interface, then we begin the MP3 player that uses that software interface. We'll use what's called synchronous mode. So this is the simplest way of controlling the sound effects that are going to be played. Synchronous mode, very simply, we'll send a message to say play this sound effect from the SD card and then stop it and then play this next one. So there's no kind of callbacks or asynchronous handling or anything like that. It's a very simple series of messages that we're going to use, because this is not complex sound effects we're playing here. We've literally got two sound effects saved on the SD card. The first one is going to be when the puzzle is first reset, or every time it's re-initialized, you kind of get a whoosh sound effect when the candles are ignited. And there'll be another second sound effect which plays when the puzzle is solved. And those are the only two sound effects. So it's very simple. And we'll declare an initial volume at which we're going to play those sound effects as well. That's defined on a scale of 0, which is quietest, to 30, which is loudest. So I've just gone loudest here. I'm going to take the output from the MP3 player into an amplifier anyway, so this value is actually not that important because it's going to be subsequently boosted through the amplifier anyway. And at the end of the setup function, we'll call reset. Reset actually sets the initial state of the game, and it's called from setup, but it's also called every time the puzzle gets reset. So that's what we've got here. So we play that sound effect, which I've just described. So we play the whoosh sound effect when the candles ignite. We loop over all the candles, and we make sure that their current status of being lit is set to true, because the default state of the puzzle is that all the candles are lit. We'll write a high signal to the LED pins. Now, remember I said that we're going to make the LEDs flicker, and we will do that in the loop function, but when we first ignite them, we're just going to send a solid high value. So they'll come on at full strength when they first ignite. They'll only start flickering in a moment. We'll put a slight delay in here so that rather than lighting up all at the same time, the candles kind of light up in order with a very brief delay in each one. I just think that looks a bit nicer, but you can take that delay out if you want, if you'd like the candles to all come back on instantaneously. We'll reset the counters, relock the lock, and we'll just say that the puzzle has been reset again. So a lot of these lines of code here are the same as what we have already done when we first declared them up here. This was the default state of these variables anyway. All we're doing is we're explicitly setting them back to be those same values again as they were at the start, just to make the puzzle back to how it was when it started. That's exactly the point of this reset function. And then we go on to the loop. So this is the final function, and it's also the main body of where the puzzle logic actually gets executed. It's not actually that hard. There's a lot of lines here, but you'll see many of them are actually just printing output to the serial monitor anyway. So we'll just step through the logic here as it occurs. So once again, we go through each of the candles in turn. And the first thing we do is we check our array of values to say, is this candle currently lit or not? Because if it's not lit at the moment, it doesn't really matter whether the player's blowing it or not, because there's no flame to blow out, it's already out. So we're only going to execute the next section of code if this candle is currently alight. And if it is, what are we going to do? Well, we're going to create that flame effect, which I was just describing. So we're going to use the analog write function, not digital write, we're going to write analog this time. And that takes a value between 0 and 255. So in this case, I'm literally just going to pick a random value somewhere in that range on every single time this is called through. Now, if you wanted to, you could limit that range slightly. So let's say you always want the candle to be at least half brightness. You could set that value to somewhere between 128 and 255 instead. And you might try different values and see what you prefer there. And we're going to write that value to the LED pin that corresponds to the candle that we're currently looking at. Because I is going to loop through from 0 to the number of candles. This is the LED pin that corresponds to the ith candle. Okay. So now we've made the flame light up. Well, now we need to work out, is this candle being blown? So for that, we need to read the input pin for the ith candle. And the sensors I'm using output a high value by default. These microphone sensors, they're normally high, but when they detect a sound, like if you're blowing to them, they go low instead. So if we read the input pin that's associated with the ith candle and that's low, well, that just means that it's heard a sound at this point in time. But we don't want these candles to be blown out by kind of, you know, random bangs in the room. Escape rooms can be noisy environments, and people can jangle keys and people can drop things on the floor and people can shout. So we want to make sure that this is actually a constant level of blowing across the microphone input. So the way I'm going to do that, and there's a couple of approaches you could do. I thought about doing a running average, for example, and sort of summing a running average over a period of time. But what I've got here actually works surprisingly well. I simply wait a short amount of time, so this is 20 milliseconds, and then I'm going to read the input pin again and check whether it's still low 20 milliseconds later. Now the point about that is that if there is a very percussive sound effect, so you know, someone clicking their fingers or clapping their hands or something like that, it would read low the first time, but then because that sound effect dies so quickly, when we then come to read the pin again later, it's probably going to read high. So this blocks a lot of false readings you would get from kind of just random bangs in the room. It means that there's a consistent source of sound across the microphone, and that's a fairly good indicator that it's being blown on. Now, obviously, this doesn't actually know that someone is blowing across the room. It could be that they're singing loudly next to the microphone or something like that. But you know, that's actually still a fairly accurate representation of what would blow a candle out. You know, if I sang close to a candle, it would blow it out. Sound, after all, is just movement of air. That's exactly what travels sound signals in a room. And that's what the microphone is detecting. So it's detecting a continuous loud sound passing across the microphone, and that is something that would blow a candle out. So if that's the case, what do? Well, we update the array for the ith candle. We'll say, okay, well, it's now no longer lit. And we'll also turn the LED off for this candle. So that's dealt with the fact that this candle was just extinguished. What we now need to do is, well, was this the correct candle to be extinguished? So to find out whether it's the correct candle or not, what we need to consider is what step of the puzzle we're currently on, and what the candle that we expected to be blown out for this step was. So at the first step, well, that's when the current step variable is 0. That's what it's initialized to when the code first runs, and that's what the value is reset to every time the puzzle is reset as well. So the 0th item in the order list, that's going to tell us the candle ID, as it were, that we want to be blown out first. and that is the 0th candle, so the one that's most on the left. Now I, at this point in time, remember that I is telling us the candle that has just been blown out. So what we're going to do is we're going to compare those two values. Is the candle that's just been blown out equal to the candle that we wanted to be blown out, given the number of steps that we've already taken in the puzzle? If it is, that means that the candle's correct and we move on to the next step. That's fantastic. If it's not, we need to keep track of the fact that the players have made a mistake. So we'll increase that mistakes made variable. And at this point, this is where you might want to modify the code to reflect how you want the puzzle to work. Remember I mentioned there's kind of two alternative methods that you might want the puzzle to be reset. You might want it to reset as soon as a mistake is made. And if that's the case, what you want to do is just uncomment this line of code here, because this section of code here is what's going to get executed when the candle that was just blown out was not the correct candle for the order in the sequence. And you might want it to reset straight away. Or if you want to let the players carry on and only discover that they've got the sequence incorrect at the end of the puzzle, put that comment line back in there and we'll carry on. So we go on to the next step in the sequence and we carry on and we go through all these puzzles, and this continues until the current step is equal to the number of candles. So what that means is that players have blown out all the candles, because this only gets advanced when a candle has been blown out. It starts off as 0, so when it's equal to the number of candles, all the candles have been blown out. And only at that point you might want to compare, well, have any mistakes been made at the point they get to the end of the sequence? If so, you might want to reset the puzzle at that point instead. So those are the two kind of places, depending on how you want the puzzle to behave, those are the two places that you might want to call the reset function. If, on the other hand, we've got all the way to the end of the puzzle, so if the current step is equal to the number of candles and the mistakes made is equal to 0, well, that means that they got every candle blown out in the correct order. So we execute this block of code here, and we will simply output some debug message to the console. We'll play the other sound effects. We'll play the second file that's saved on the SD card of the MP3 player. We'll unlock the lock, and then finally what we'll do, we'll just wait a short amount of time and then we'll call reset again. So this is an auto resetting puzzle. Once it's been solved for a certain amount of time, yeah, I mean, you could extend this to, if you want a significantly longer lock period, so you could make this, you know, a minute, 20 minutes, however long you want. But rather than having to manually reset the puzzle again, we can just wait a certain amount of time, then call reset again, and then that will behave just as it was when the puzzle is initialized. All the candles will light up once more, and the counters will all reset to 0. So that brings me to the end of this tutorial. I hope you found it interesting or useful, and perhaps it's given you a new idea for a puzzle that you can use in your escape room game. I think candles are a great prop that can be used in many different escape room settings, whether it's a medieval or an Aztec tomb or something mystical and supernatural. But ultimately we've got to consider safety first, and real candles are not normally an option. But I think these LED candles offer a pretty good substitute, and I've given you one example of the way that they can be used as the basis for a puzzle. As always, I want to say thank you so much to all my Patreon supporters who enable me to make these tutorials each month. I want to say thank you very much for your ongoing support. I will, as always, upload the Arduino code and the wiring diagram and the list of parts that I'm using over on my Patreon page. So if you'd like to head over there to check them out, please do so. And if you are able to, and if you'd like to support me to make more of these videos in the future, that would be very greatly appreciated. Otherwise, if you have any comments or suggestions, please do write them below and I'll do my best to get back to you. And I just want to say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.